Alrighty, gang, welcome back. Today is our last day of regular lecture for Calc 1. So you guys have more or less made it through the gauntlet. We are here. Today, we're going to formally cover section 6.1, which we informally covered most of on Friday of last week, because there's not, frankly, a whole lot to it. But there is a little bit more to it than we saw. So today, we're going to talk about areas between curves in a more formal sense. Remember, your exam 3 is our next class meeting this Wednesday, and that leaves Friday open to review for the final exam. So let's start with those little date announcements, make sure everybody is on the same page. This is MAC 2311, section 004, which is a Calc 1 class. The date today is the 18th of April, 2022. And what we're doing today is areas between curves, section 6.1. Announcement-y stuff. Of course, exam 3. Is this Wednesday. Which is the 20th. Focus. Oh, damn it. I will be doing a makeup session for this exam, but it's not going to be like the other ones where you've got like 3 or 4 or 5 days between. If you really need it, if you really need it, I will offer a makeup on Friday in office hours. So it just gives you 2 extra days. I know sometimes at the end of the term, when shit's crazy, 2 extra days is like, whoa, big difference. But it's not a huge chunk of time, and we are kind of in this era where if you've been keeping up and you're in good shape, then you really don't need to worry. And if you haven't, then 2 extra days probably won't make a huge difference, but I know there are those circumstances. So Friday in office hours is 1 p.m., normal link in Canvas. Y'all know the drill. Your final exam. Let's see, for this class, I was looking at it earlier. Final exam is the 26th, which is the following Tuesday. And it is at 3:30 p.m. So be aware, not our normal exam time, 3:30 to 5:30 p.m.
It's still online, right?
I know there were some people who had conflicts between the final exam for this class and the final exam for chemistry. I've spoken with a few professors in the Nat Sci department and the Nat Sci chair. The chemistry exams, if you have a conflict, will be moved. You'll have an alternate testing date for chemistry. I know sometimes biology, BSc 2010, has a conflict with this class as well. Check your schedules, right? Check your schedules, make sure you know when your final exams are scheduled. The general rule is that when a science and math final conflict, science bends, math stays. But you need to talk to your professors and make sure you know exactly what's going on. If you miss the final, you miss it, and there's really not much I can do. What else? Study Guide 3 has been up for a while. Study Guide 3 will be due on the 20th, right? So if you want feedback on that study guide before the test, get it to me as quickly as you can. If you get it to me by like tomorrow afternoon, I can try to give you some feedback before the day of the test. On that Wednesday, I will not have time to go in there and mark up any study guides. So the latest I could possibly put any comments on the study guide would be like Thursday evening, or sorry, Tuesday evening, tomorrow evening. I think that's it.
Study guide for the.
We can talk a little bit about areas between curves. So last time we saw that if you have a pair of curves, maybe something like f g, and you want to find the area between these bad boys, say from A to B, you put A here, and B here. If you want to find the area bounded between these two, then really all you have to do is integrate the upper function minus the lower function from A to B. So these will be definite integrals. And you'll integrate the larger guy minus the smaller guy. So the area between them you can think of it as the integral of the blue minus the integral of the red, and it doesn't matter if one of them dips beneath the x-axis or not. It's worth noting that if you're to do the integral of the red here, this area would be measured as negative, and when you subtract it, it would become positive. So this comes out to, regardless of the orientation, integral a to b of the upper minus the lower. In this case, that would be f of x minus g of x dx. And people always remember this as the upper minus the lower. In practice, we saw that you often have to solve for these intersection points. Maybe because you want like all the area enclosed between the two curves. So you would need to integrate from this x value to this x value. And that would mean you need to solve for the x values of those intersection points. We also have seen that if the curves were to trade places, like here, maybe if I wanted the area between those curves from here to here, from like here to here, then you'd have to do two separate integrals, because who is the upper and who is the lower, they swap. I think we mentioned that, but didn't look at an explicit example, so I'm going to see one of those for you. And then we're going to take a look at what happens when your curves are not defined as functions of x, but perhaps as functions of y, or maybe not even specified. Maybe you're given an equation like x times y equals 1, and you have to figure out what to do. So let's take a crack at this. Let's say note. Often we need to solve for intersection points. By solving the equation f of x equals g of x. This is one thing. Another, the upper and lower can trade off, requiring us to split up the integral. And I'll say one other thing. I don't even want to write it down because I don't want to confuse you, but I want to say it. The textbook defines the area between the curves f and g as the integral of the absolute value of f minus g. They put absolute values here, and they don't care who's the upper and who's the lower, or whether they trade places. Formally, that's correct. But in practice, the only way to calculate an integral like that is to find the intersection points and split it up, depending on who is the upper and who is the lower. So you may see in your homework integral of absolute value of f minus g. And just know that the way to handle such a thing is the procedure that we've been discussing. You find the intersection points, sketch the region, figure out what area you're after, and then in each of the different sub-intervals where one is the upper and the other is the lower, you'll calculate a separate integral. Let me show you exactly what that looks like. So, yeah. So a classic problem here is to find the area between sine and cosine from 0 to pi over 2. Say f of x equals sine x, and g of x equals cos x, x equals 0 to x equals pi over 2. Is there a study guide for the final? I have to remember whether I built 3 or 4 study guides in your guys' class. Study guides, no, just 3 of them. Yeah, so this exam 1, exam 2, and exam 3 study guides. I think I might have a review for the final exam for you guys. So let me just put a quick pause on this. I used to work for UF. And I wrote these big review packets for them when I worked there. So let me see if they still have those. I think, yeah. This is mine, right? Yep. All right. So here is a nice review for the Calc 1 final. It's short and sweet, but it's got all the good stuff. And I think I wrote, yeah, I thought I had yeah. Oh, I see. And somebody else added some other shit here and they don't know law tech. Okay. So yeah, I would say if you are comfortable with these problems, you should be in pretty good shape for the final exam. I can post those to Canvas. Let's get in here and try to solve our problem. So with all of these area between curve problems, you should sketch the region, right? We did solve one the other day without drawing the graph, and the question was, is it necessary to always draw the graph? I would borderline say yes. And it's true that you can kind of hack your way there without drawing the graph in some cases, but it is wise to always draw the graph. So I need the sketch graphs of sine and cosine. The easiest way to do that. Yeah, whatever. We'll call that pi. Nah, let's call this pi over 2. We'll scrub this. We'll call this pi. Yeah. Okay. So for sine, here would be pi over 4. This would be 3 pi over 4. Sine, I'll do in this blue color. You know, the sine of 0 is 0. I'll put 1 up here. Sine of pi over 2 is 1. Sine of pi is 0. So sine is going to go through a half period in this graph I'm drawing from 0 to 1. And then back down to pi. And of course, sine continues off this way and does this thing. It's off this way. That's all well and good. So here's the first half period of sine. Cosine, I'll graph in red. You know, cosine of 0 is 1. It's going to start up here. Cosine of pi over 2 is 0. And cosine of pi will be negative 1. We can go up to pi here. So the cosine function is and continues off this way, doing its thing. This way, doing its thing. All right. So cosine in red, sine in blue. I want the area from 0 to pi over 2 bounded between these curves. So the area I'm looking for is this stuff plus this stuff. And what you notice is that who is the upper and who is the lower swaps between 0 and pi over 2, which is the interval I'm trying to work on. So there is no consistent upper and consistent lower. So the area I want, I'm going to call this A1 and call this A2. Be A1 plus A2. A1 would be the integral of the upper minus the lower from 0 to pi over 4, right? We know pi over 4 is the intersection point here. I haven't had to solve for that, where our sine and cosine equal. The first positive solution is pi over 4. So either from the graph or from remembering your unit circle or however you think about trig functions, hopefully we're all aware that sine and cosine are equal at pi over 4. So A1 would be the integral from 0 to pi over 4 of the upper function here minus the lower function here. The upper function is cosine and the lower function is sine. A2, I'll calculate in a second. Let's go ahead and grind this out. So I need an antiderivative for cos x minus sine x. Antiderivative for cos x is sine x. Antiderivative for sine x is negative cos x. So I'll have minus negative cos x makes plus cos x. And this gets evaluated from 0 to pi over 4. At the upper bound there, sine and cosine are equal to each other. They're both root 2 over 2. So this will be root 2 over 2 plus root 2 over 2. And then minus at the lower bound, sine is 0 and cosine is 1. Everybody good so far? So if you differentiate sine, you get cosine. If you differentiate cosine, you get negative sine. So this is my antiderivative. Plugging in pi over 4. In fact, we get plugging in 0. Root 2 over 2 plus root 2 over 2 is 2 times root 2 over 2, which is just the square root of 2. 0 plus 1 is 1, so we're subtracting 1. So there's A1. A2 is the same sort of bullshit, only now I'm going to integrate from pi over 4 to pi over 2, the upper minus the lower here. The upper, remember, blue is sine, red is cosine. So on the second subinterval here, from pi over 4 to pi over 2, I'm going to integrate sine minus cosine. Pi over 4 to pi over 2, integral of sine x minus cos x dx. Same sort of antiderivative stuff. Antiderivative for sine x is negative cos x minus an antiderivative for cos x is sine x. And we evaluate this from pi over 4 up to pi over 2. Just a little more space on this. Bump this up here. So if I plug pi over 2 in here, let me give myself just a little more horizontal space. At pi over 2, cosine of pi over 2 is 0. Sine of pi over 2 is 1. So this is going to be 0 minus 1. And then I subtract from that what I get at pi over 4. Cos of pi over 4 and sine of pi over 4 are root 2 over 2. So this is negative root 2 over 2 minus root 2 over 2. So it's negative 1. And then negative root 2 over 2 minus root 2 over 2 is negative root 2 minus negative root 2 becomes plus the square root of 2. Therefore, the total area I wanted was A1 plus A2, which is the square root of 2 minus 1 plus negative 1 plus the square root of 2. And you notice it's root 2 plus root 2 is 2 root 2. And then minus 1 plus minus 1 is minus 2. So that is the area between sine and cosine from 0 to pi over 2. It's double that first area. And you might be able to see that in the symmetry here, right? A1 and A2 are actually equal. My picture isn't perfect, but they're both root 2 minus 1. Questions on the setup here? Questions on the execution? All right. I'm going to play with your mind geometrically a little bit. Let's just see what I remember. What does the curve x equals y squared look like? Anybody have a grasp on what this might be? Yeah, very good. It is a parabola. Just like y equals x squared is a parabola, x equals y squared is a parabola. What's the difference between this and the normal y equals x squared?
Would it be that the parabola is symmetrical on the x-axis rather than the y-axis? Like it's been turned 90 degrees, essentially.
Sort of two ways to think of it. You can think of this as the normal y equals x squared parabola, but reflected over the line y equals x, because you're swapping x and y. Or you can say x equals y squared is the same as saying plus and minus the square root of x equals y. The positive square root of x, looks like this. Negative square root x is just this. So together you get a sideways opening parabola, right? Together, these are x equals y squared. So if I was drawing x equals y squared on its own, just as itself, I would say it looks like this. It's the y equals x squared parabola, but instead of opening up and down, it opens to the right. All right, and the horizontal axis is the x, vertical axis is the y. In other words, just turn your head 90 degrees to the right. Try not to break your neck. The reason I'm showing you this is because sometimes problems relating to areas between curves are best thought of with respect to the variable y rather than with respect to the variable x. So another question, can I set up an integral for the shaded area let me call this the point 1, 1. Here. Of course, the answer is yes, right? What we're really asking is how do you set up an integral for that shaded area? This would be the integral from this y value, which is y equals 0, up to this y value, which is y equals 1, thinking of the function as having little Riemann rectangles in here like this. The area there would be the integral from y equals 0 to y equals 1 of y squared dy. See, it's the same as the integral from 0 to 1 of x squared dx. It's the same fucking thing. It's just turned sideways, right? All right, and people don't usually write the y equals with the bounds. I like to write it that way to emphasize that the bounds are coming from y values here, but you could just write it like this, and most people do. So with that in mind, we can start finding areas between curves where perhaps one or both of them are given as functions of y rather than as functions of x. And the tricky biscuit is figuring out whether you're going to do the integral dy with the variable as y, or whether you're going to do the integral dx with the variable as x. So let me grab, I think there's a reasonable example like this in your book. Here's the formal Riemann sum stuff. It is often helpful to think about a little Riemann rectangle in here because that can inform whether you're going to set up the integral with respect to y or with respect to x. Let's not make life harder than it needs to be. This is a good one. 1/2 y squared minus 3. So x minus 1 and y squared equals 2x plus 6. Let's between y squared equals 2x plus 6 and x minus 1. So the first thing you want to do is sketch these. All right, you want to sketch the curves and have some idea what you're looking at. The fact that there's a y squared in one of these is a pretty strong hint that we're going to end up integrating with respect to the variable y, but we still want to take a look. Because this is a y squared thing, right? Linear in x, quadratic in y, it's going to be a sideways opening parabola. We should solve for x. So this means y squared minus 6 is equal to 2x, which means 1/2 y squared minus 6 is equal to x. And you might be trying to remember, how do you graph such a thing? You can always plot some points if you want. So we can see where we're at when y is 0. If y is 0, then this is 1/2 times -6 is -3. So y is 0, that means we're on the x-axis. Let's go to -1, -2, -3. And because there is no linear term here, no linear y term, that's going to be your vertex. The roots would be at plus and minus the square root of 6, right? If you set this equal to 0, you've got x equals √6 and x equals -√6. So I'll just call this right here the square root of 6. It's right here, -square root of 6. So here's that parabola. And something like this. And then the line y equals x minus 1, you know that. That's a line with slope 1, y-intercept -1. Square root of 6 is definitely bigger than 1, right? So -1 is going to be like right in here. Exactly how big is √6? That's bigger than 2, right? So we'll do, so this is 1, 2. And I'll put this guy in a different color to help him stand out. So 1, you know, something like this. So first step, make sure you know how to graph, right? Make sure you know how to graph these curves. It's not anything crazy. If you need to review it, review it. There's stuff all over YouTube. Just Google graph sideways parabola. Let's shade the area. Once you have your picture, it's much easier to figure out how you're going to set up your integral. Is there an upper and a lower here? Is it kinda, not really, right? Like, sure, here the purple is the upper and the red is the lower. In fact, everywhere to the right of this intersection point, you could say the purple is the upper and the red is the lower. But what about over here? The purple is both the upper and the lower. You could hack your way there by saying you're going to find this area as upper minus lower. integrated from whatever this x value is to whatever this x value is. And then over here, you could say, I'm going to calculate the area kind of above the x-axis and double it because there's this symmetry over here. But that's sloppy. Instead, turn the picture over. Now there's an upper, and this doesn't look like it's shaded, but it is. Ought to be. Now there's an upper and a lower. The red is the upper and the purple is the lower. But you don't want to do the whole homework set with your head like this. So instead, we adopt the convention that if you're working with respect to y, you integrate the right minus the left. So if I can draw, and this is why you see those little strips being drawn in, the little Riemann rectangles. Son of a bitch, that better not be my mortgage lender. I will kill her. 10 seconds. Ugh, don't buy a house. It's a pain in the ass. Just don't do it. I'm kidding, of course. Do it. It's a good financial move. It's just a royal pain in the ass. So we want to think of this area as being filled up with infinitely many little rectangles like this. And the idea is that this is now your height, right? Instead of the height of your rectangle being like a vertical distance, it's this horizontal distance. And the kind of width of your little rectangle here is dy or delta y. And we integrate the right minus the left. So when working with respect to the variable y, we integrate from the smallest y value in your region to the largest y value in your region, right function, because it has the larger x values are going up that way, minus the left function, dy. You will need to learn to set these up. The very beginning of Calc 2 is an extension of these thoughts where you then revolve these regions around some axis to get a solid and you find the volume of the solid. There's no escaping this skill. You got to do it. I know it's a bit of a headache at first, but you practice it and it won't be so bad. So for the problem we're looking at, that means I need to know the y value here and the y value here. I need those intersection points. You can find those intersection points by taking this thing solved for x and setting it equal to this thing solved for x. So y equals x minus 1 is the same as saying y plus 1 equals x. And then I will solve for my intersection points over here. That means I'm going to take 1/2 y squared minus 6 and set it equal to y plus 1. And notice that the answers here are going to be y values. That's what I want, right? I want to go from the smallest y value in my region, A, to the largest y value in my region, B. I'll start by multiplying both sides by 2, and that'll give me y squared minus 6 equals 2y plus 2. Then I can pull everything to one side, and I'll get y squared minus 2y minus 6 plus 2 is minus 4 equals 0. And, oh shit, are these horrific numbers? Minus 6 minus 2. Sorry, this should be a minus 8. Okay, yeah, minus 6, and we subtract the 2 over minus 8. All right, that's better. So this is going to be y minus 4 times y plus 2 equals 0. So we get y equals -2 and y equals +4 as our intersections, right? So the y value here, this is y equals -2. And the y value here, this is y equals +4. So my integral is going to be the integral from -2 to 4 of my right function as a function of y, being solved for x, which is y plus 1, minus my left function, solved for x, which is 1/2 y squared minus 6 dy. I'm putting each individual function in parentheses. On this problem, it's not necessary, but I want to just do that to remind you that you're subtracting the whole functions as chunks. Here, it wouldn't affect anything because we have to distribute the 1/2 anyway. Let's go ahead and do that algebra then. I'll have y plus 1 minus 1/2 y squared minus 1/2 times -6 is plus 3 dy. And then I like to put these in order and combine any like terms. You should at least combine the like terms. So this is -1/2 y squared plus y plus 4 dy. And then our antiderivative, y squared would integrate to y cubed over 3, or 1/3 y cubed. -1/2 times 1/3 is -1/6. So I have -1/6 y cubed. The y term is going to integrate to 1/2 y squared. So I have plus 1/2 y squared. And the 4 will integrate to 4y. And this needs to be evaluated from -2 up to 4. So this is the bulk of the work for the problem. Before I get into just the arithmetic of carrying out that evaluation, I want to make sure we're all comfortable with this part. So questions like up to this integral. Are we quiet because we're comfy, or are we quiet because we're afraid to ask? Don't be afraid to ask anything. I promise you, the first time I saw this shit, I was like, what the fuck?
Is it always going to be right minus left?
Let's go ahead and do the evaluation then. We can go with bringing this up here. So at the upper bound, I'll have 1/6 times negative 1/6 times 4 cubed is 64. So I'll write that as negative 64/6 plus 1/2 times 4 squared. So that's plus 16/2. Plus 4 times 4 is plus 16. Minus. Let's see. So 64/6, negative 64/6, that's 4 cubed over 6. Oh, no.
Sponsorship relies on the
Ah, I
same
was
logic.
muted. Okay, I'm sorry. Let's go back. I did not realize I was muted. Thank you for the heads up there, Shona. So, yeah, questions through the setup. Let's come back here.
Is it always right minus left?
Yes, it is. Yep, just like when you're integrating with respect to x, it's always upper minus lower. Integrating with respect to y, it will always be right minus left, because the larger x values are over here and smaller x values are over here, just like larger y values are on top and smaller y values are on bottom. So yeah, always right minus left. Was there anything else that I missed there? Okay. Let's continue with our evaluation. When we plugged in 4 here, we got negative 64/6 plus 16/2 plus 16. When we plug in negative 2 cubed is negative 8. So that will make this a positive 8/6. Negative 2 squared is positive 4. 1/2 times positive 4 is plus 2. And negative 2 times positive 4 is minus 8. So I've got negative 64/6 minus 8/6. That's negative 72 over 6. 16/2 is 8. 8 plus 16 is 24. And I grouped this guy with this guy, so they're done. And then I've got plus 2 minus 8, that is minus 6. So that's negative 72/6 plus 24 minus 6 is 18. 18 as a ratio over 6, what is that? That is 60 plus 6 times 8 is 40, 100. So I've got negative 72/6 plus 106, is that correct? 6 times 8.
I think it's 108.
42, isn't it? Yeah, so 102, sorry about that. Yeah, 60 plus 42. Okay. And then when we subtract 72 from 102, let's see, that's the same as 70 from 100. Is that 30 over 6? Is this arithmetic correct?
I think the 18 is supposed to be a 108 instead of a 102.
Oh, is it? Let's see. Oh, it is. Yeah, 48. I'm sorry. 40. Where the fuck am I getting that? 108. And that will change this. So then 108 minus 72, I'm just not risking my brains melted today. 36. All right, I'll take it. 36.6. Hey, that's nice. Who would have thunk it? All right. So sketch the region and then integrate right minus left. The thing you need to be careful about, as long as you're comfortable sketching the region and the rule integrating right minus left, is finding your bounds, right? So the right minus left thing, both of the curves, equations, whatever, have to be solved for x. And the bounds need to be y values. So these should only have y's in them. And the bounds need to be the smallest y value in your region to the largest y value in your region. Let's try one of these where it's not clear what we're going to do, integrate with respect to x or y. Before I move away from this particular example, any questions about any part of this process?
Is this going to be on this upcoming test or only on the final?
Good question, just on the final.
Okay.
Yeah, so the cutoff for the material that's on exam 3 is the exam 3 study guide, right? That's the stuff that's going to be on there. So the stuff that goes up through last Wednesday.
Will we have a homework set for this?
Yes.
Okay.
Yeah, there is no dedicated study guide for the final, so there will be one last homework set here. And it will be on areas between curves. Maybe a little bit of extra use sub practice thrown in for good measure. What looks good here? I like number 9, 1 over x, 1 over x squared, and x equals 2. Those are some pretty wonky looking things. And these are curves we should know how to sketch, right? These are in our parent functions file that we've had. Even the MAC2311.004 parent function file that was in there from the beginning of the semester had these. File, Desmos graph. Nice amount of space here. And we'll start with 1 over x. I'll mark this point as 1, 1. What does 1 over x squared look like compared to 1 over x? Oh, that's not blue, that's purple. All right, we'll do purple. So x equals 2 is a vertical line. Let's do that one next, and then we can kind of use this as a guide. X equals 2 is a vertical line, and the intersection point with 1 over x, you just plug in 2 for x here, that's 2, 1/2. Where is 1 over x squared going to be when x is equal to 2? You plug 2 in here, what do you get?
1/4.
1/4, right? Which is smaller than 1/2. So 1 over x squared at the intersection with x equals 2 is down here. Where is 1 over x squared going to be when x is equal to 1? What do I get if I plug 1 in here?
Still 1.
Still 1. So these guys have the shared intersection point of 1, 1. But then 1 over x squared is smaller here. So what we're looking at is something like this. And this is something you should remember, that 1 over x squared dives down faster than 1 over x. 1 over x cubed dives down faster than 1 over x squared. If you plot, this is a fun looking plot, I can't resist. If you plot 1 over x to the n for a bunch of integers n, they all have this kind of shared shape. Here's 1 over x. Here's 1 over x squared. 1 over x, 1 over x squared. Right, and as you increase that power, you see they dive down faster and faster and faster. This is going to be an important thing when you learn about convergence. So we're told to find the area of the region bounded by these 3 curves. And here it is. And if you draw in your little Riemann rectangle, you see there is a defined upper and lower all through this region, so it makes sense to draw the rectangle oriented up and down like this. So I'm going to do my integral with respect to x, because I do have a clear upper and a clear lower everywhere here. So this area would be the integral of the upper curve, which is 1 over x, minus the lower curve, which is 1 over x squared dx, from the smallest x value in my region, which is 1, to the largest x value in my region, which is 2. So built into the problem here was like sketch the curves, figure out whether to integrate with respect to y or with respect to x. And from here, it's a cakewalk, right? From here, we know exactly how to do these integrals. You may write this as integral 1 to 2. I'll leave the 1 over x alone. We all know what to do with that. But maybe x to the negative 2 is the better way to write the second piece, because here requires the power rule, whereas the first piece is a natural log thing. So this will be the natural log of the absolute value of x. When you take an antiderivative for x to the negative 2, you add 1 to the power, giving you x to the negative 1, and then you divide by that power. So this will be minus negative x to the negative 1, or plus 1 over x. We evaluate from 1 to 2. At the upper bound, we get the natural log of the absolute value of 2. Well, the absolute value of 2 is just 2, plus 1 over 2, or 1/2. And then I need to subtract from that the natural log of the absolute value of 1, which is just the natural log of 1, plus 1 over 1, which is 1. Natural log of 1 is 0. So this is the natural log of 2, plus 1/2, minus 1. So the natural log of 2 minus 1/2. It's about 0.19.
If you were,
Yeah, go ahead.
yeah, if you were given, so I understand it's three like functions. If you're given like, let's just say three different polynomials, would you just set up a system of equations to find the intercepts?
That's one option. I would start by giving a rough sketch, right? Like try to graph each one on their own and, try to graph each one without doing too much work to have a feeling for where area is being enclosed. But then to find intersection points, you don't need to find where all three curves intersect at once, right? Like if we tried to do that here, if you set up a system where you have all three curves as the equations, or all three equations as the pieces of your system, you would be asking for a point where all three of those curves intersect simultaneously. And you notice here, that's impossible, right? This point,
Right.
them touch this one. So what you'd be doing is setting them up pairwise. You would set one equal to another. You'd set up all possibilities of one curve equals another curve, and that would find all possible intersection points. But I would give a rough sketch of the graphs first. So because you might be able to see right away, oh, one of these definitely doesn't fuck with this other intersection point. Like you can see kind of roughly which of those pairs of equations you need to set equal to each other.
Okay, thank you.
Yeah, of course, of course. Other questions on this one? Okay. Let's fiddle with a couple more. The rest of these are kind of easy. There's something a little harder. 11 or 12 both look good. Between 11 and 12, any choices? Okay, I'll pick. Let's do 11. That one's tagged as special. So we've got the two curves, x equals 1 minus y squared and x equals y squared minus 1. Some nice symmetry there. So again, I need to begin with a graph. I'll put 1 minus y squared in red. And y squared minus 1 in teal. If you plug in y equals 0, then you get x equals 1. So the red curve goes to the point 1 comma 0. And if you factor this, this is 1 minus y times 1 plus y. So we have y-intercepts up here at 1 and down here at -1. So this parabola has to be looking like this. Modulo my bad art, something like that. The other guy is almost, well, it is literally the negative of that. If you plug in 0 for y here, you get x equals -1. And he factors as y minus 1 times y plus 1. So he has the same roots, which in this case means the same y-intercepts. So he's going to be looking like this. So the area I'm after is this area. So I want you guys to help me out here. Let's start with the integrand, the function that goes inside here. What goes in here?
Would you set it up like in 4 different quadrants to get the area, or?
We could exploit an awful lot of symmetry here, right? I could find just this area and then double it. I could find just this area and multiply by 4. But let's go ahead and pretend like we're gonna just follow the rules blindly without trying to exploit any symmetry. So I'm going to integrate the right minus the left from the lowest y value in the region to the largest y value in the region. So what would my right?
1 minus y squared.
Very good. The right function is 1 minus y squared. And I need to subtract from that the left function, which would be
Y squared minus.
very good, y squared minus 1. And this is done dy. Remember, always write your differentials at the end here. I will have to take off points if you get sloppy and leave those off on the test. So please always write those. And then what are my bounds of integration going to be? What's the smallest y value in this region?
-1 to 1.
Very good, right? Down here, this is what tells me my lower bound. Up here, this is what tells me my upper bound. So integrate from -1 to 1. 1 minus y squared minus y squared minus 1. Again, the first parentheses isn't necessary, but do you see why the second one is? I need to subtract this whole function, which means this negative is going to get distributed to these two terms. So make sure you don't skimp on your parens either. So this is integral -1 to 1. I have 1 minus y squared plus 1, which is minus 2y squared plus 2 dy. And it's true, we could get away with a lot less if we used some symmetry. I could just do one integral to find this area, which would be the integral from y equals 0 to y equals 1 of the 1 minus y squared curve, and then multiply by 4. But this is the sort of natural way to set it up without exploiting symmetry. An antiderivative for -2y squared would be -2/3 y cubed. And an antiderivative for +2 dy, be careful here, this is not 2x, it's 2y. I know it's very easy to get in the habit of, like, you see a constant, you write that constant times x. Just remember, we're working with the variable y here. And we evaluate from -1 to 1. At positive 1, I'll have -2/3 times 1 cubed. 1 cubed is 1, so this is just going to be -2/3, and then plus 2 times 1 is 2. Subtracting what we get at the lower bound, that's -2/3 times -1 cubed. -1 cubed is -1, so it's negative times negative makes +2/3. Plus 2 times -1, oh, I should have just written -2. So what do I have all together here? I've got -2/3 minus 2/3, that's -4/3. And then +2 minus -2 is +4. And you could write this as a single ratio. 4 is 12/3, so 12/3 minus 4/3 is 8/3. And that's our boy. I don't think we have time for another full problem, but we can take a quick peek at some of these and discuss how we would set them up. Before I do that, are there any questions on the graphing, the setup of the integral, execution of the integral, anything?
So if we're working with respect to the x-axis, basically it would be upper minus the lower, and if we're working with respect to the y-axis, it would be the right minus the left.
Perfect. Yep, that's
Okay.
exactly correct.
Cool.
Good. All right, let's take a quick peek here. So this guy, would we do this with respect to x or with respect to y? Number 3. Is there a well-defined upper curve and lower curve? Or is there a well-defined right curve and left curve?
With
Could you do it
respect-
either way?
I think this one we necessarily need to do with respect to y. So this red curve here would be our right, and the blue curve here would be our left. So yeah, the blue isn't being like the upper here, right? There is no clear upper or lower between blue and red in here or over here. The blue is playing both roles of upper and lower here. The blue isn't even involved in the boundary here, and the red would be the lower, so that doesn't work. But the red is everywhere to the right of the blue. So here we would integrate e to the y minus y squared minus 2 from -1 to +1. What about number 2 here? Is this going to be a dy thing or a dx thing?
dx.
Yeah, here there is no always clear right and left. It does look like the blue curve kind of sits to the right of the red curve most of the time, but then I've got this boundary here at the left is 0. So like above here, you could treat the blue as the right and the red as the left, but below down here, the blue is the right and nothing is the left. But the red is always above the blue. So here you would integrate the red minus the blue from 0 to, what would my upper bound be? I'd integrate from 0 to where?
1.
Very good, 1, right? Because that's the largest x value in this region, the x value of this intersection point. All right, so with that said, I think we're ready to wrap up. And that, guys, means you finished Calc 1. Like, pat yourself on the back. This is more knowledge than most humans on the planet have. We're not completely out of the woods yet. You've got exam 3, you've got the final. That's a lot of grade right there. So make sure you prep hard for exam 3. Exam 3 again is Wednesday. It's our next class meeting. So make sure you show up on time. Make sure you're ready to get into honor lock, have your ID ready. Make sure your phone is charged so you can get into the Zoom meeting and you don't have to hop out. If you have any testing accommodations, make the appropriate preparations. If you need anything from me, come see me in office hours. Today's office hour is over, but I do have another one tomorrow from 11 to 12. And that's it from me. Any burning questions before I end the meeting?
Are we doing the review for final on Friday?
Yes. Yep.
Okay.
So Wednesday is going to be exam 3, and then Friday will be review for the final. We can do whatever you guys want on Friday. It'll be your day.
Are we gonna meet on Monday again for the final or no?
I don't believe so. No. So you guys' final is the 26th. So the official last day of class is the 22nd, and then your final is the 26th. So that Monday, we're not going to have a class meeting. Classes are technically over on the 22nd.
That means no office hours as well then?
I'll see what I can do. So I can't promise steady office hours through here because I might have to give a final at that time on Monday. But if I'm not actively proctoring a final, I'll hold an office hour. Look to the announcements for that. I'll go ahead and prep an announcement right now with the final exam review that we talked about and information about the office hours. Any other questions before we go? Okay, I'm going to go ahead and end the meeting here. If you need anything from me, you guys know what to do. Otherwise, I'll see you on Wednesday for the test. Make sure to get questions ready for the final exam review on Friday. That's it. Take care, guys.